The first convex hull algorithm that I would like to look at is gram scan. This is one of the simplest convex hull algorithm that it works very nicely in 2D. So assume that I have a point set in 2D given to me by x and y coordinate. In other words, the point pi is given to me by coordinate xi and yi. And I have this as an input and I have stored them somewhere that I can access them. Okay? The first thing that I do in this algorithm is to sort these points by x coordinate in increasing order, which means that the first point in the list will be the point with the smallest x coordinate and the last point will be the point with the largest x coordinate. And then what we do here is to initialize a few things, and the algorithm is essentially an iterative algorithm. Okay? So we'll use a variable or a data structure called UH to represent the upper hull. This algorithm only computes the upper hull of the convex hull, and then of course if we can do the same thing, like for example by flipping the points to compute the lower hull and then attach them to each other. So this upper hull is a data structure that will store the vertices. So it's just a list. So this thing is just a list of vertices. Okay, and then we will actually see what kind of operations we'll need this data structure to support. But before understanding the remaining steps of the initialization, I will need to talk about what invariant this algorithm requires or has. The main invariant is that in this iterative algorithm, so I'm going to fill in the contents of this for loop here, right? You'll see a for loop starting from 3 to n. At the ith iteration of the loop, or at the iteration I, which means when the variable has value I, we have the upper hull of the points p1 up to pi in the variable upper hull. That is what we want to achieve. This means that when I equals n, when we finish the last iteration by I equals n, then by the invariant, I have the upper hull of all the points p1 up to pn inside this variable, which is exactly what we want. Okay, so if I can maintain this invariant from one iteration to the next iteration, then I'm done. And this s is just, I put it for the size, right? You don't necessarily need it if your data structure implicitly has size of UH. So let's see some examples of what this invariant means. Okay, so imagine that I'm looking at the points one by one. This is equivalent to revealing the points of the upper hull one at a time from left to right. So the first point that gets revealed is the point with the smallest x coordinate. So that gets revealed. That obviously is part of the upper hull, so I can just add it to the upper hull. And as you can see here, the first 2 points I added automatically to the upper hull because there is no point in iterating over the 1 points because we already know it will be part of the upper hull. Okay. Similarly, if the input point has only 2 points, then the upper hull is just both of them. So that means that's easy. Okay, so if the first 2 points have been revealed, they are part of the upper hull. So that's why my for loop starts from number 3 or I equals 3, because for the first 2 iterations of the for loop, I really don't have anything to do. So now let's say we look at iteration number 3, or when I equals 3. So this means that the third point in my list gets revealed, and that's that point. When that point gets revealed, I can clearly see that this edge is the upper hull edge, and that point does not belong to the upper hull. Which means at the end of the first iteration of the for loop, or iteration number, when I equals 3, the upper hull should only have 2 vertices, that vertex and that vertex. Okay. So in general, how does this look like? How do we do the iteration? So let's say this is a general case. In the general case, we have an upper hull. So we have an upper hull of everything from I equals 1 to I minus 1. So this is point 1, and this is point I minus 1. Everything to the left, essentially, these are all the points from 1 to I minus 1. We have an upper hull. So the UH stores this list of vertices. Okay. Then at the ith iteration, what I do is this. Don't read this. I'm going to explain what this means. I add the iteration. I add the point pi. In this picture, what I can see here is that this point pi creates this upper Hall edge. So the upper Hall should be this new chain that looks like this. And this point should be removed from the upper Hall. And this while loop tries to do that. How do we know when a point does not belong to the upper Hall? It's actually quite simple. We just need to look at the 3 last elements of the list in the following sense. So we have the point pi, so that's the point I'm adding. So let me change the... Okay, so let's say this is point pi that I'm adding right now. This is the last point in the list, in my list UH. So this is the element number S in UH, and this is the one before that. Remember that these are part of the upper Hall so far, by the definition of, or by our invariant. Okay. In other words, UH contains S elements, 1, 2, S minus 1, and S. I look at these 3 points, US minus 1, US, and PI. If this makes a left turn, then I know that S is not part of the upper Hall, because you have an upper Hall that goes like this, and then you look at the last 3 vertices, say this one, and say this one. You can see that if I have a left turn, then the middle guy cannot be part of the upper Hall. In general, when you have an upper Hall that goes from left to right, you're always making right turns. That is the geometric observation that is used to create this algorithm. When you follow these arrows, you can clearly see that these arrows are turning to the right. So therefore, you should never see a left turn when you follow the upper Hall from left to right. Which means if you see a left turn, then that point should be removed. But it is possible that you need to remove multiple points. So for example, if I have a situation that goes like this, it's at this point, and this point, and if I add, say, a point over here, then all of these 3 points should be removed. And basically, the way to code this is to do a while loop. So you look at these 3 vertices, it's making a left turn, so you remove this, and then you look at these 3 vertices, it's still making a left turn, you remove that. Look at these 3, it's making a left turn, you remove that. Let's say this is making a right turn, so we add it to the list. Okay. So the basic algorithm is relatively simple. Let me just erase my annotations. As long as the last 3 elements of the list, well, the last 3, pi and the last 2, make a left turn, we remove the middle one. Once that is, when the condition is no longer the case, then we can safely add pi to the list. There is also additional constraint, and that is we should check that there are at least 2 points left, just because then otherwise this S minus 1 will be meaningless, right? So we need to have at least 2 points left. If there is only 1 point left, then we can just add pi to the list. Okay. And at the end of this iteration, we can add pi to the list and increase the size of the upper Hall by 1. And so that's it. That's the gram scan. The only thing left to do, well, the correctness of this algorithm is more or less obvious because we are maintaining the invariant. So we're going to look at well, it's actually easy. You can think about the proof, but if you have questions about the proof, you can look at it as an exercise during the class. But the correctness of this algorithm is not really difficult to show. And actually, the running time is also not difficult to analyze, right? So let's look at the running time. The first step is a sorting step, which obviously takes some log n time. And then in the middle part, we can see 2 embedded while loops. So this while loop could run n times. An example is that you have an upper Hall that goes like this, and then the last one, let's say, is over here. It's all the way up, over here somewhere. And now everything needs to be removed, and then maybe the convex hull becomes something like this. Okay, so it is possible for this interior while loop to run n time. So the naive analysis will be that, okay, this while loop runs n time, the for loop runs n time, so this is an n squared algorithm. But that's not a very good analysis. A better analysis is to say that during this while loop, every point is removed at most once, because once we remove a point, we don't consider it again. And also every point is added at exactly once, or at most once. So therefore, every point is considered only a constant number of times. So therefore, this entire iteration takes linear time. So therefore, gram scan is a linear time n-log-n algorithm, but only because we need to sort the points. If somebody gives us the points in sorted order, we can actually compute the convex hull in linear time, and that's actually pretty cool.